we are solving a huge nonlinear system of equation fx equal to 0, where we have the same number of equations as the unknowns, just as we had on the last page, right? 3n plus 3 unknowns, 3n plus 3 equations. So the assumption is that we are given a x0 that doesn't have to be the solution, but close in some sense. So if I know I have x0 that is close to x, is there anything I can do to get to a better solution that is even closer to x?
Subtract the error.
Yeah, subtract the error. So if we have a x0 that is close to x, we can evaluate, we can substitute that x0 and evaluate f of x0, right? And although I don't know what x is, I know what f of x is. What is it? 0, right? That's the equation, right? X is the unknown solution, but I know f of x is 0. So if I can substitute 0 with f of x, the whole thing is something I can compute, right? I'm going to call this residual. It's called residual because if the goal of the Newton iteration is to drive the residual smaller and smaller and smaller and ultimately to 0. If the residual is equal to 0, I call myself converged, which means I have found a solution that satisfies fx fx close enough to 0. So this is something I can compute. I can also expand this into Taylor series. Okay, I expand it to Taylor series. The residual is actually written into as that. So it's the minus of what I'm looking at. So now if you expand it into Taylor series, basically expand the f of x around fx0. What you have is fx is equal to fx0 plus fx0 prime times x minus x0 plus high order terms. Right, these high order terms are why you need an x that is close enough to the solution to start with. So if these high order terms are 10 to the 11 or something, right, then this equation is not much better than nothing. All right. Okay, so now let's assume x and x0 is close enough such that the high order terms, although not negligible, is not as big as the first order term. Then from this equation we can substitute into here and get something useful. So this minus this is simply going to be the substitute f prime of x0. I can approximate it with this minus this. Here the f prime is a matrix, right? It's a square matrix. Okay, it's every column of f prime is the derivative of every equation with respect to the same variable in x. Every row of f prime is going to be the derivative of a single equation to all the variables involved in the equation. And this matrix times x minus x0, which is a column matrix, should approximate the residual I can compute. Now, from this approximately equal equation, how can I find a method to get a better approximation to x?
So just rearrange the equation by dividing out the f prime on the other side.
That's right. So the Newton method is saying that, okay, so this is an approximate equality, right? And that means x minus x naught can be approximately written as this inverse times f times just the minus of fx0, right? Okay, that means if I can define my x1 to be just the x0 plus what I have on the right hand side of this equation, then potentially x1 is going to be a better approximation to x than x0. Alright. In fact, if you look at this, the difference between x and x1 is actually going to be just the f prime inverse times these high order terms I neglected in the Taylor series. So if the high order terms are small compared to the first order term, then this x1 is going to be a lot closer to the real x than my original x0. Now we don't have to stop here, right? My x1 now is a better approximation. So it's a better x0 than x0. So the iteration continues. My x2 is going to be x1 plus f prime of what in this case? x1 now, right? Times minus f at what? x1 now, right? So I forget about x0. It's a worse approximation to x than x1. So I'm going to use x1 for everything here. Now my x2 is a better approximation to x than x1. So this continues. So basically my xn plus 1 is equal to xn plus, well, let me just write minus because I just want to move the minus out. xn inverse times f xn. A good thing about Newton method is that when it doesn't work, it doesn't work. Because, I mean, you have a terrible initial guess, it just doesn't work. But if it does work, if you do have an initial guess that somehow is good enough, it converges really quickly. And this is actually how I usually debug, I mean, not debug, but like identify, is there a bug in my Newton's method? Like, because sometimes writing a code of computing the Jacobian is not always that straightforward, as you can see when you come back. We're going to actually write a code to construct the Jacobian. Even for that simple equation, it's not straightforward. If I have a bug, often Newton's method still converges, but you're going to see that it converges exponentially. That's counterintuitive. Exponential convergence is usually fast, right? So if things goes down, okay, I get 0.1, 0.01, 0.001, 0.0001, I'm usually very happy. But if your Newton's method converges like that, you probably have a bug. Because Newton's method usually converges actually faster than that. You may have 0.1, 0.05, 0.02, and 0.002, and suddenly 10 to the minus 8 and 10 to the minus 16. Things like that should be what you expect. So when it converges really, really well. And I haven't seen a lot of situations I need more than like 10 to 15 Newton's iterations. If you computed everything to machine precision, right? Sometimes like the Jacobian is close to singular and you can't really, I mean the solving the linear system doesn't really get you that good answer. In that case is that the Newton's method may converge slower than what you expect. But like if the Jacobian is good, and the Newton's method should converge really, really fast.